All right, thank you very much. Can you hear me? The microphone's on? Okay. So thanks very much to the organizers, in particular to Thomas, for setting up this very nice workshop. So I'm going to talk about a couple of papers. So this basic idea actually is rather old. It goes back to a paper in 2009 with Eric Bergschuff and various people. But we have sort of started to understand more recently that this has a very nice mathematical interpretation, which, well, I don't think I have to justify the use of mathematical structures to this audience, but I think that really simplifies various things. And I will talk about some work in particular that I did more recently with Henning Samtleben, who's in the audience, and my postdoc Roberto Bonezzi from Berlin. And many of these structures we discuss were also discussed by Thomas and collaborators, so I will cite this in the right moment. So here's the overview. So I will be guided by the, okay, I lost the pointer again. Okay, well here it is, but it's not doing much. Okay, well, all right. Anyway, so we'll be guided by the central question whether we can formulate physics in terms of first-order duality relations. So that's a theme that is rather old, but there's some sort of new interest in this. So the first part of this talk will be a brief discussion of what duality relations are. So I basically want to give you the big picture at the start. And I will discuss the notion of the tensor hierarchy briefly, which shows up in formulations of gauge supergravity and this concept of exceptional field theory that Henning discussed already briefly. So that's sort of the physical, so half physical picture behind this. And then I will discuss the mathematical structures, so this thing which we call the duality hierarchy, which is based on a differential graded Lie algebra. So I will introduce where this comes from. And this whole concept can be derived from some notion called the embedding tensor, which was originally discussed and introduced in gauge supergravity, but for which we have more recently understood how we can rethink exceptional field theory, that I will briefly review, in terms of such an embedding tensor. Okay, so that's the overview. So let me start right away with the first part, the duality relations and the use of the tensor hierarchy in this context. So what's the duality relation? So let's start with something simple. Let's start with a free scalar theory, let's say in 3 dimensions, just for definiteness. So here's a free scalar with the usual equation box phi equal to 0. And so a first-order duality relation reinterprets this equation as the integrability condition of a first-order relation between the field and a dual field. So here you see a duality relation that is first-order derivative. So you write d mu phi is epsilon mu nu rho f nu rho, where f nu rho is the field strength of an abelian vector field. So you have a gauge symmetry introduced here. And this relation is such that if you hit it with another derivative, so you act with partial mu, you get 0 on the right-hand side identically due to the epsilon tensor, so that drops out. So that then tells you that the left-hand side is 0 too, which of course just gives you the box phi. So in this sense, you have obtained the usual free massless field equation as an integrability condition of a first-order differential equation. Something similar you can also do for gravity, more precisely linearized gravity. So we take Einstein gravity, expand it around the flat background, eta mu nu. H mu nu is the massless spin 2 field, and then you have first-order Einstein equations. And it so happens that you can rewrite these first-order Einstein equations, meaning you take the first-order piece of the Einstein tensor g mu nu, and you pull out one derivative. So this differential operator, or this tensor, has the property that it can be rewritten as the divergence of a new tensor y in this way, which has 3 indices, and which is defined as a first-order object in derivatives given here. So this h bar is just a particular combination of h mu nu and its trace. And you can check that if you take the divergence of this object, you get the linearized Einstein tensor. So that means instead of writing the linearized Einstein equation, I can write a different equation, a first-order duality relation that relates y mu nu rho to the Hodge dual, so to say, in the same way as for the massless scalar, in terms of a new field D that in D dimension carries a block of D minus 2 antisymmetric indices and one extra index. So that has mixed Young tableau components. But now it's again of this type that if you hit it with a derivative, on the right-hand side you get 0 because of the epsilon tensor and the partial derivative here. So as an integrability condition, you obtain the linearized Einstein equation. Or you can also get a second-order field equation for this new field D, which is the so-called dual graviton. So these are two well-known instances of rewriting physics in terms of first-order duality relations. But of course, in general, there are obstacles. You can't always do this. So let's discuss this next. So let's make it slightly less trivial, and then you immediately encounter problems. So let's consider again a scalar field, but now with a non-trivial potential. So then there will be a source term in the field equation. So that will be some arbitrary function of phi, depending on the potential v. And now, of course, the right-hand side no longer has any derivatives. So it doesn't make sense to ask whether you can pull out a derivative in order to write a first-order duality relation. So in the same sense as before, you cannot write this equation as a first-order duality relation. And something similar happens for gravity. If you go beyond linearized gravity, you get a source term on the right-hand side. So you can rewrite the nonlinear Einstein equations as we always see them as sort of a flat space expansion. So you start with the linearized piece of the Einstein tensor, but of course non-linearly you generate also quadratic, cubic, etc., higher order terms of the Einstein tensor, and those I bring to the right-hand side. And then there's also, can be of course an energy momentum tensor of any matter fields. And again, this equation has the property that you cannot pull out a derivative on the right-hand side, although here it is less obvious because these objects do have derivatives in it. But the point here is that if you could pull out the derivatives, those terms would be sort of so-called improvement terms of the energy momentum tensor, which are considered to be trivial. So this was something pointed out by these people also a while ago. So again, we cannot write nonlinear gravity in terms of first-order duality relations, at least not in the naive sense that I've introduced in the previous slide. Okay, so now how can we get around this? And this is the mechanism that actually shows up in gauge supergravity and also exceptional field theory, how the duality relations work in this context. So what's happening here is that you don't have a single duality relations, rather you have a hierarchy of first-order relations. Whether you still want to call them duality relations or not is, of course, just a matter of semantics. But the basic mechanism is this. So in gauge supergravity and exceptional field theory, we encounter non-abelian nonlinear field strength, which are of this schematic form. So you have a normal, familiar kind of field strength. You have a bunch of nonlinear terms, which are like Yang-Mills terms that are not looking at into the moment, but there's also typically an extra coupling to higher forms. So if you start with the one form, A mu, there's typically a coupling to a two form, B mu nu, that comes under a certain operation. So this is this frac D, which I keep quite generic at this point, but which will satisfy various relations that I will discuss during this talk. And because of this extra term here, the Bianchi identity in general is modified. It takes a hierarchical form, and that's sort of one reason why this is called a tensor hierarchy. So if you take the curl of this new field strength calligraphic F, you don't get 0, as you would get for Yang-Mills or Maxwell. Rather, because you act with the curl on this guy too, you get the frac D of a new field strength, which is the field strength of the two form. So it's a three-form curvature for the two form, and that shows up on the right-hand side. And what this means is that you can now write duality relations or derive nonlinear field equations as in gauge supergravity as the integrability conditions of a set of several duality relations. So going back to the example I had 2 slides ago, let's look at the scalar. Now we write the covariant derivative of phi is the Hodge dual of this new field strength, this non-abelian and modified field strength. But on top of this, I postulate another relation, namely that the 3-form field strength, or it's rather its Hodge dual, is a certain function of the scalars phi, which I assume here can be chosen in such a way that acting with this black box operator calligraphic D, frac D on F, gives me the source term of the Klein-Gordon equation with the potential, so it gives me the V prime phi. And so you can see how this works. If I take the first relation and I hit it with a d mu, I can use the right-hand side of this relation, move the d mu inside. Usually in the free theory I would get 0 here by Bianchi, but now I don't get 0. Rather I get this frac d acting on h mu nu rho by the Bianchi identity up here. And now at this step I can use the second duality relation. I can use epsilon mu nu rho h mu nu rho is d of f, frac d of f, which I assume can be chosen such that this is just v prime. So then I've obtained a second-order, nonlinear second-order field equation as the integrability condition of 2 duality relations. As I said, so I get the nonlinear scalar equations in this example of gauge supergravity. And it's kind of pleasing that we know, in fact, in gauge supergravity and also in exceptional field theory, the gauging procedure that introduces this nonlinear field strength and the tensor hierarchy with their hierarchical structure, they are correlated with the fact that you also have a scalar potential, which shows up in the source term. So in gauge supergravity, these things always go together. And that is precisely what you need in order to write duality relations. So this is the very basic mechanism in one example. And now I want to develop a general theory of how to formulate these relations. Okay, if there are no questions so far, then let me change gears now. That was just sort of the general picture. Yeah, Mark?
Wait, there's a question. Next time I'll do that. So you will have also equations of motion for a mu and for h mu nu rho. I mean, what is the number of degrees of freedom? They are algebra. I mean, they are auxiliary fields. Is it guaranteed?
Well, it depends, of course, on the theory. If you consider 3-dimensional theories, you can go up to 3 forms, which, of course, have trivial curvatures. And so in general, you have an entire chain of forms to all degrees, and you can write.
My question is, so you start with the Klein-Gordon equation with a potential, so you have a definite number of degrees of freedom.
Yeah.
Are you introducing extra degrees of freedom in this procedure, or the number of degrees of freedom is unchanged?
So no, the number of degrees of freedom should not be changed, and you can see that. So, for instance, let's look at 3 dimensions as an example. There we know all the degrees of freedom are encoded in scalar fields. But in the gauging procedure, you have to introduce vector fields too that make it non-abelian. But in 3D gauge supergravity, they only come with Chern-Simons couplings. So they themselves never carry propagating degrees of freedom. And so in that sense, you have not, in the deformation of going from the ungauged to the gauge theory, you have not changed the number of degrees of freedom.
Maybe to be more precise, probably you need to assume that it's local, right? Because if you add global, you get some global modes in addition. By these dualities, right? You assume always the Poincaré lemma to be true.
Yes, I usually assume that, right? But but I think your question was in the sense of local propagating degrees of freedom, right? There can be, with non-abelian gauges and higher gauge structures, of course, there can be new phenomena that are due to the global nature of some gauge fields, for instance. That is possible, yes.
No,
I don't have much to say.
Already on the first transparency, right? When you introduced your a mu, I think you have this phenomenon. There can be whatever parallel transports around some non-trivial cycles if the topology is non-trivial, and it's not equivalent. It's equivalent locally if it's contractible or something.
Yes. But the first slide. I mean, in form language, all I use is d squared is 0, right? At this point, I don't think I've used more than that. But yeah, but of course, what your comment is still correct, of course. Okay. Any other questions before I continue? Okay, so then let me now change gears a little bit and develop the general mathematics behind it. So that's the structure that are underlying gauge supergravities, the non-abelian gauge structure, which I have not shown in the previous slides, and which was just represented by dots in the field strength. That non-abelian gauge structure can be understood as so-called Leibniz algebras. So the gauge algebra of gauge supergravity, exceptional field theory, double field theory are governed by Leibniz algebras, which are certain generalizations of Lie algebras. So Lie algebras are special cases, and in which case we get back to normal Young-Mills theory. That's, of course, good, but these structures are slightly more general. And the way this works is that you have a vector space with a bilinear map that I here denote by a circle, and which is the generalization of the Lie bracket, but which is not assumed to be antisymmetric. So you have a bilinear operation, which in general has a symmetric and an antisymmetric part, but it does satisfy a cubic relation, which is basically a substitute for the Jacobi identity. So you have this relation here, and this I guess also tells you where this name Leibniz algebra comes from, because if you think of vectors acting on other vectors through this circle product, then this relation just tells you that the vector v here on the left-hand side acts via the Leibniz rule on the right-hand side. And so why is this a good structure to look at? This is the minimal structure in some sense that you need in order to have consistent symmetry variations, infinitesimal symmetry variations. In the sense that if you define an operator LV, I called here, just by this circle product, so V acts on W via this Leibniz product, that those can be interpreted as consistent infinitesimal transformations in the sense that if you work out the commutator now on a vector, you get a symmetry transformation of the same kind, except that the effective parameter here is just V circle W. So this is just the analog of the fact that the adjoint representation of a Lie algebra is a representation, and that's just the consequence of the Jacobi identity. And here you have the same relation, except that this Leibniz identity here is the only thing that is used. Now, the difference to Lie algebras is that in general you may have a symmetric part. So here I defined the symmetric part of the Leibniz product, so I symmetrize by hand. It's also denoted by these, the anti-commutator notation. And it's convenient to think of this symmetric part as being decomposed into two more operations. So I introduce an operator frac D, which plays the same role as this operator I had in non-abelian field strengths on previous slides. And the new bilinear symmetric operation, which I call a bullet here, which maps this original vector space, which I called x0 here, into a new vector space x1. So what we're doing here is we take the original space on which the Leibniz algebra is defined, and I interpret the symmetric part of the Leibniz product as being a certain map D, which will be interpreted as a differential in a second, and a new symmetric operation bullet here. So, of course, you could say, well, this symmetric part...
Is it always possible to write this symmetric part as a composition of
yeah. Yeah, it's...
Can you repeat the question for the online?
Yeah, so the question was whether I can always...
Yeah, I'm sorry. I think it's better to ask it so that it's online. Is it always possible to write this symmetric part as a composition of frac D and this dot product?
Yeah, thanks. It's a good question. Of course, the question is, what do you demand of these objects? So far, I haven't assumed anything. So if I don't assume anything, then of course it's always possible, because you may just say frac D is just it says take a second copy of the original space. I say frac D is the identity and bullet is the same as the circle. That would be sort of a trivial way of doing it. So unless I specify further rules, it's not so clear, but, or it's trivially possible. I guess the more important question is to what extent is this unique? Because you start with the symmetric, or to what extent is this canonical? Because you start with the symmetric part of the given Leibniz product, and now you want to decompose it into two parts, one operation frac D and one bilinear operation. What fixes that? And I don't really have a very good answer to that, except that in all examples you always look at, particularly in exceptional field theory, there's always a natural choice. And in exceptional field theory, this always works because the frac D becomes a differential operator and the bullet becomes something algebraic. So it's just something with some group theory, tensors constructing some objects. So in examples which I will give later, it's always obvious what you have to do. But I'm not sure how to formulate this in a very sort of, in a very mathematical way that would just give you a very general prescription of how to do that. So that's is an assumption here, if you like, namely that you can, yeah. So what we do here is we introduce a larger space now. Okay, now I lost again the. Okay. Well, anyway, you can read the slide. So, so we introduce now a larger space, and we will start building up a higher algebra on this larger space, which will take have the structure of a chain complex, namely, here it is again, namely that you have a sequence of spaces, and the numbers here, the subscripts, will denote the grading, so there will be an internal degree to all these vectors. And there will be differentials D mapping between these spaces and squaring to 0. So as I motivated now the first space you introduce, you start from the Leibniz algebra, you have a space X1 that is mapped back with this operator D. And now the structure that appears in gauge supergravity and exceptional field theory is that you potentially have an infinite chain of spaces here and more differentials. And you have extensions of this bullet product and the circle product that have to satisfy all kinds of relations. So one thing we did in one of these papers last year with my postdoc Roberto was just to try to identify what are all the algebraic relations you need between the differentials and the bullets, so that the construction of the tensor hierarchy that before we've always done on a case-by-case basis can be formulated in generality or abstractly. And so we succeeded at doing that in this paper. But it turns out that there's actually a much simpler prescription, characterization of these structures, and that's in terms of so-called differential graded Lie algebras. Now, before I come to that, let me discuss the so-called embedding tensor. So in the previous slide, I've introduced the Leibniz algebra just abstractly as the structure that emerges, the gauge structure that emerges in gauge supergravity. But it turns out that one can derive it, or in all gauge supergravity construction, it actually comes from a genuine Lie algebra and a so-called embedding tensor map. And that's a construction which controls the whole formulation of these theories, and hence is useful, in fact, also in exceptional field theory. So how does this work? So you start with a Lie algebra, so you have a Lie bracket. So whenever you have a Lie algebra, it comes equipped with an adjoint and a coadjoint representation, which I denote here. So zeta and A are both adjoint vectors. So this is the usual representation is given by the Lie bracket itself. And then the dual or the coadjoint representation I denote by at star here. And this coadjoint representation is defined in such a way that if you take a dual vector and a vector, or an adjoint vector and a coadjoint vector, you have a pairing that just gives a number, that this pairing is invariant. That's sort of the definition of the condition of the coadjoint representation. Okay. Now, in the embedding tensor formulation, I need something more general. I need to specify, in addition to the Lie algebra, I need to specify two things. I need to specify a representation of this Lie algebra, which I call R here. And I need to specify the so-called embedding tensor map. So what's the embedding tensor? It's a map from this representation space R into the original Lie algebra. And why is this needed, this map? It's needed because this gives you a way to sort of transport or move the Lie algebra structure on the original space of the Lie algebra to a bilinear operation on the representation space R. And the way this works is very simple. So you want to define a bilinear operation between two vectors v, w in R. So these are vectors in this representation space R. And you do this by taking the first vector. You use the embedding tensor map theta to map the vector into the Lie algebra. But once you're in the Lie algebra, you know how to act on the second vector. That's just done by the representation you've assumed to exist. So this rho zeta here is just my notation for the representation operator. And so I have this operation. Now, this is a bilinear operation, not anti-symmetric in general. And this defines a Leibniz algebra, provided I obey a certain quadratic constraint, which is written here, and which is a kind of compatibility condition between the circle product and the original Lie bracket. So the condition is that if I take this Leibniz product of two vectors to get a new one, I map it to the Lie algebra via theta, then the result is the same as if I take the two input vectors via the embedding tensor to the Lie algebra and then take the Lie bracket in the Lie algebra. So that's a natural compatibility condition. And you can prove very easily that if this holds, if the quadratic constraint is satisfied, then this circle product here indeed defines the Leibniz algebra in the sense that it obeys the relation I had on the previous slide. Okay, so there's also just a side remark here. There's also an alternative way to write the embedding tensor, or to think of the embedding tensor, which I write as capital theta, which is as a map from R tensor G star, the dual of G, into R. So sort of a dualizing or raising and lowering of raising and lowering of indices. This is defined by this pairing here. So it's in the finite dimensional context where we write things with indices, this is obviously the same, but in more general or infinite dimensional context, it may make a difference. But if this pairing here, this map into R, is invariant under the Leibniz action, then also this is in fact equivalent to the statement of the quadratic constraint. Okay, so that's just a very abstract definition of the embedding tensor construction, which gives you a Leibniz algebra. And now I come back to the original program. So the program, remember here, was given a Leibniz algebra, or given a Lie algebra and an embedding tensor, which then gives you a Leibniz algebra. Can you sort of construct this algebraic structure on a chain complex that is needed in order to construct tensor hierarchies? So that's the program. So that means I have a series of these bullet operations on a potentially large vector space, a graded vector space, of which we have seen here at the beginning. And I want to identify what are the relations you need in order to define a tensor hierarchy. Okay, and one can write this down. And it turns out that this has a very nice and natural interpretation, and it's just what is called a differential graded Lie algebra. Okay, now I lost again the... Okay, anyway, so let me read it to you. There it's back. Very good. Shouldn't lose it again. Okay. All right. So actually I haven't given you here the definition of a differential graded Lie algebra, so for this audience it's probably not needed, but so I can just say it quickly in words. So a differential graded Lie algebra is a graded vector space where you have a graded symmetric or asymmetric bracket that satisfies a graded Jacobi identity. So that's like a superalgebra, we all know. But you also have a differential that squares to 0. So that maps, like as given here, between the vector spaces of different degrees. So here in my conventions, it would have degree -1, so it lowers the degree, but that's just a matter of convention. And you have compatibility conditions between the bracket and the differential. So the differential acts on the bracket just by the graded Leibniz rule, as you would naively expect, and the differential squares to 0. So that's the structure. And it turns out that this graded symmetric bullet operation that I introduced before can in fact be interpreted as a graded symmetric bracket of a differential graded Lie algebra. Technically, that involves the notion of suspension, where one shifts the internal degree of all spaces by +1 or -1, in order to make sense of this operation being graded symmetric rather than being graded antisymmetric. But that's just the technicality that teaches you how to keep track of the signs. And so the structure then that emerges, you see here's this chain of vector spaces. So in this new picture, this suspended picture, the Leibniz algebra sits here. So in my convention, it is a space of degree 1. There's the original frac D that I introduced the slide before that maps from a higher space that is now at degree 2. So I go from x2 to x1. But with the embedding tensor construction I showed on the previous slide, I can actually extend the space further, and this makes the whole construction very intriguing. I can, in fact, write another differential D that is just the embedding tensor map. It maps from the space of the Leibniz algebra, which was the representation space of the underlying Lie algebra, to the Lie algebra itself, which I've now included as a space at degree 0. And of course, formally, I can just extend it arbitrarily to spaces x -1, etc. And I know what the relations are. And in this language, the Leibniz algebra itself, more or less the same way as on the original slide, is derived from this underlying differential graded Lie bracket, or the bullet operation, via this formula here. The signs are just need to be fixed in some way. And as before in the embedding tensor constructions, the Leibniz relations follow from the general axioms of a differential graded Lie algebra. And in this construction that includes this Lie algebra G, the entire chain complex forms a representation space of G. So all of these spaces here now are particular representation spaces of the original Lie algebra G. Okay, so that's the mathematical structure that is relevant here. So now let's try to formulate a gauge theory given that structure. So we start with a differential graded Lie algebra of the type I just described, so which I call X. And now I want to introduce p-form fields. They take values in this algebra X. So I tensor this X with the space of all differential forms on some underlying manifold M. So that could be anything, any dimension. And it turns out that this total space, which now consists of differential forms on some space-time manifold M, taking values in this DGAL X, that these are the elements I need for the tensor hierarchy. And this total space itself also, in fact, carries the structure of a differential graded Lie algebra. And this comes about because you can define a new differential now. Because you have differential forms, you have the de Rham differential D here, but you also have this frac D, the differential of the original DGLAX. And the sum of it, you can check, also defines a differential. And you can extend the graded Lie brackets to the bigger space with the differential forms. just by, you get a bunch of extra signs, of course, because now you insert differential forms. But one can show that there is, well, you have, first of all, now a double grading. You have the degree of the differential forms, which I denote by these subscript in square brackets, like 0, 1, 2. These are the form degrees. And then there's the superscript, which is the degree of the original space X, the DGLA. So I have a bigrading, and I have differentials frac D going horizontally, and I have the de Rham differential going vertically. And with respect to a diagonal grading, which is K minus P, K being the original DGLA grading and P being the form grading, this is actually another differential graded Lie algebra. So I've, in these spaces here, this maybe looks a little intimidating, I've also indicated here in which spaces various objects of the tensor hierarchy are located. So for instance here, I have one form gauge fields. So these are the analog of the Young-Mills gauge vectors we all normally have. But then, as I explained before, there are also two forms, A2, three forms, etc., and it never stops. So this is sort of diagonally sitting in here are the fundamental gauge fields. Then I have at the next level here, I also have the field strength, which are related by the differentials. And I have gauge parameters here and trivial gauge parameters, or gauge parameters for gauge parameters, etc. So they're all part of this big DGLA. So I can now formulate the tensor hierarchy, and coming back to the duality hierarchy of the beginning, very neatly in terms of this very large space. So as I said, I have a differential graded Lie algebra with respect to this diagonal degree. So I combine, so you should think of this here as combining all forms into formal sums. So you take here the A's. Here is just the formal sum of one forms, two forms, three forms, etc., potentially going on forever. The F's are the formal sums of two-form field strengths, three-form field strengths, etc. So in this way of writing it, I remember only the diagonal degree, which is indicated here. And I have this structure of the DGLA, differential graded Lie algebra, with the gauge parameters or formal sums of gauge parameters sitting here, gauge field sitting here, field strength sitting here, and then you could also have Bianchi's, etc., etc. Okay, so those are the basic objects. Now let's look at this Mara-Cartan-like form omega defined here. So I built e to the minus a partial e to the a. Now this is a little formal because it's not so clear, I guess, what you mean by exponentiating an object in A, which is the formal sums of forms. But all we need here is sort of the application of the Baker-Campbell-Hausdorff-like formulas for these pure gauge-like objects. And the fact that if you allow yourself to use these, then you find that this identically satisfies the Mara-Cartan equation. That, of course, we know. If you have an object like this, you have the Mara-Cartan equation. And so all these was observation, in fact, pointed out in this paper a while ago. So the interesting thing here is that the simple Mara-Cartan equation that holds trivially for this object omega here, in fact, encodes the hierarchy of Bianchi identities that we do have in exceptional field theory and gauge supergravity. And the way this works is that you identify the non-abelian field strength F of the tensor hierarchy as the omega piece plus a contribution. You have to take out sort of something non-covariant. You have to take out the one-form gauge fields via the frac D. And if you then rewrite this relation in terms of the F's, and you decompose explicitly into the differential forms, you get a relation that can be written like this, where the bracket here is the DGLA graded Lie bracket of the structure we have. And you see this is precisely the structure, the hierarchical structure of the Bianchi identities of the tensor hierarchy that I sketched before. So I take the exterior derivative of a p-form field strength, which is suitably covariantized, which is the D here. And then there are some sort of non-abelian, non-linear contributions, but this is then related to the frac D, to this other differential of the next higher form field strength. So if you remember from the beginning, very schematically, I explained here this Bianchi identity where the curl of a field strength, here two-form field strength, where it did not specify any of these terms, gives rise to a frac D of a field strength of sort of the next higher degree, so two-form going to three-form in this example. And if you go up in form degrees, these relations, of course, become more and more complicated, and with more and more nonlinear terms that in this example we didn't actually see. But it turns out that all this nonlinearity is very neatly encoded into this sum of the underlying the differential graded Lie bracket. And this whole thing here is just a rewriting of just the Morra-Cattan equation. So that came to me. I've worked for many, many years with these Bianchi identities and the tensor hierarchy. So that is just a sort of rewriting of the simple Morra-Cattan equation came to me as a big surprise. So that's sort of a neat observation, and I think it shows the strength of identifying the proper underlying mathematical structure, which here can be thought of as a differential graded Lie algebra, because it allows you to recognize how you should package the objects. Yeah.
There's a question.
So the objects that float on the whiteboard are reminiscent. It's probably a naive question. Reminiscent of, for one thing, the Cartan model of equivariant cohomology, and de Rham cohomology, equivariant de Rham cohomology, where you basically get such sort of forms with values in the Lie algebra, and then of Lie algebra cohomology, where you valued in a module of a Lie algebra. So the question is, can this be somehow packaged nicely or extends? I don't follow fully, so this is a genuine question. Can it be packaged nicely in terms of these structures? Lie algebra cohomology. So you had a module for Lie algebra. Right.
Space R.
So with this you can immediately associate Lie algebra cohomology valued in that module, and then the objects you constructed are sort of reminiscent of a Cartan model of equivariant cohomology. So I wonder if the formulae that you sort of write and structures that you build up are somehow related to these two.
It could well be. I haven't thought about it, but maybe we can discuss it afterwards.
Because they typically arise my point is that they typically arise when you try to gauge symmetry. So for example, when you go to the sigma model and you gauge its configurational symmetries that come from isometries, lifting isometries of the target space, then you, for one thing, you end up with equivariant cohomology that encodes the gaugeability conditions, and of course the Lie algebra cohomology encodes the small gauge anomaly, basically. So somehow these are objects that are in this universe, hence my question.
Okay, I don't have a good answer at this point, but yeah, that's an interesting suggestion. Any other questions? Okay, so then let me continue with, so here I've discussed so far just gauge fields, so starting with one forms, two form gauge fields, etc. And I've identified the tensor, the crucial equation of the tensor hierarchy, which is this hierarchical Bianchi identity, as in this language, which is written here. So what I want to do next, which also comes back to my initial example of the scalar field, is to include the scalar field in this construction, the scalar fields in this construction. And this is something that sort of, I think, the most intriguing aspect of this construction, that you can include them at the same level. So, so here we introduce scalar fields, and they will, in a moment, be interpreted as parameterizing a coset space G mod H. So first, it's very natural in this structure to introduce scalars, because we have the Lie algebra as part of the space, which is the space X0. And so there's actually no reason why you shouldn't just introduce zero forms. We had all forms, so in fact you should introduce zero forms. So you have scalars in the construction. And it turns out that this parametrization as written here is the convenient one that gives you nice formulas. So we define now the omega in this form. It is still of this sort of pure gauge kind of form, which means it still satisfies the Mora-Cartan equation. But let me just rewrite this slightly so that it satisfies the Mora-Cartan equation. Can be equivalently stated as saying that I can define a new differential, which is the old differential I call partial, plus the omega, and that this squares to 0. I can now work out this new differential, that's a convenient object, in terms of the fields A and the scalar fields phi, and what I get takes this structure here. So I still get the sum of all p-form field strengths that I had before, but they are now dressed by a matrix V. So the matrix V, or calligraphic V, is in fact a group valued matrix. It's e to the phi. Remember, phi is Lie algebra valued. So that's sort of the kind of matrix you introduce whenever you discuss nonlinear realizations. So that's the V here. And then I have two objects P and T here, which are defined by this equation here. So I take V minus 1 dV. D is the normal space-time derivative, but covariantized with the gauge field. And I decompose this into two pieces, P plus Q. And this is also what you do in nonlinear realizations, where Q lives in the subalgebra H, which is the Lie algebra corresponding to a subgroup H. And P is the complement of this. So sort of in standard language would be the non-compact part. So here, of course, you have to give me additional data. Originally, we had only the Lie algebra G. Now I want to build a G mod H, so I have to pick a subgroup that defines then the coset space G mod H, and I have to define the subalgebra H. So that's additional data, but given this data, I can make this decomposition P plus Q. So the P shows up here. And then there's a new object T showing up, which is known in gauge supergravity as the T tensor, and which is obtained by this equation here. So you have a theta, which in gauge supergravity is what we think of as the embedding tensor. And this formalism is defined by this formula here. So you have V minus 1 frac dV. So this is an algebraic thing. It's not a space-time derivative. And this you rewrite as it reinterpret this as a new object theta bracket with phi. And this object lives in the space x minus 1. So this is one of these extra spaces we had. So the details here don't matter too much. There's a particular way to identify a tensor theta, which is the embedding tensor. And then the dressing with V gives you what's called the T tensor. So that's just for the gauge people who have seen gauge supergravity that may be familiar. Otherwise, you don't worry too much. And here is now now going full circle. Here's the description of the duality hierarchy. As for instance in gauge supergravity, but in principle also in exceptional field theory, as the tau of duality relations, just using these structures, DGLAs I introduced before, plus two more data I need to specify. So if I'm in n external dimensions, so I have to, of course it matters in which dimensions I am, whether I'm 3 and 4 and 5 or whatever. I need to assume that there are the following extra data in order to write duality relations. One is a series of G-covariant isomorphisms between different spaces of the complex. So we had this chain complex with the spaces X, and I need to assume that the dual of the space with degree P is actually equal to the space at degree n minus P minus 2, where here n, again, is the number of external space-time dimensions. So if you look at concrete gauge supergravity models, you see that this is always obeyed, and in fact, in these tensor hierarchies, these spaces are just the same. As representation spaces of the underlying Lie algebra, they're just the same spaces, but here, of course, we have a degree attached to it, so we don't want to forget about it. So that's why we phrase it in terms of an isomorphism that carries an intrinsic degree p. Now, that's one point we need. The second point is that we assume an H-invariant metric, H being the subgroup of G, thought of as a map from the space to its dual. And this map, this metric, in fact, is just the extension of the kind of metric you would use in order to define what's called the generalized metric by building, taking V transpose. So if you have an SON type sigma model, this is just a Kronecker delta, so you just build V transpose. But in general, you need a metric in the middle. And so if you know nonlinear sigma model, you know this construction. But what we assume here effectively is that this generalized metric is extended to a map on the entire space X. So you have such M in the representation space of any of these spaces X. Now, assuming these structures, I can write duality relations, which now just take this very simple form here. So F, this full field sum of field strength, is star IMF. And you can, going through these axioms, you can check that this works all degree-wise. And the claim is that the integrability condition of this relation implies the nonlinear equations of gauge supergravity, and that's the part that is very interesting, I think, including the nonlinear scalar equations with a right scalar potential, which in this language just takes this form here. So you have the T-tensor from the previous slide, and you have one of these maps delta. You can build this thing, and that encodes the scalar potential of gauge supergravity. So you get all equations. 10 minutes? Okay, that's enough, thanks. So you get all equations.
I have a question. This curly M, does it use all these delta P's or just delta 1 because it's extended?
No, so you have M's for each space. So you have an M1, which is the normal one, with normal, the one people usually write, but then also an M2, M3, etc. for all the deltas you could possibly have, which in concrete examples just means you have objects with more indices, which you just take together several copies of M's, for the basic M, so to say, and build higher ones.
But does it mean that you have a scalar product on each of the vector spaces of the complex?
Yeah. And it has to be H invariant, but not necessarily G invariant, right? Okay, so this is that's the general structure of duality relations, which give you all kinds of nonlinear equations, including scalar equations, and the basic mechanism is the one I explained at the beginning. Okay, so now let me come to the last part of the talk, unless there's some urgent question before. Okay, if not. So the final part is now to explain how this abstract formulation of Leibniz algebras, the associated differential graded Lie algebras and tensor hierarchies, and the formulation of duality relations, how in fact an exceptional field theory, which Henning briefly introduced on Monday, can be understood in the same language. So the construction works as follows. So you may or may not remember from Henning's talk that in exceptional field theory we define a notion of generalized diffeomorphisms, which do not satisfy a normal Lie algebra, but which in fact do satisfy what I defined as a Leibniz algebra before. So you can just look at these explicit formulas that have been written over the years, and they do not define a Lie algebra, but they define a Leibniz algebra. So now the question was, can you think of this also as coming from a genuine Lie algebra via an embedding tensor construction? So I had this construction of Leibniz algebras in terms of a real, genuine Lie algebra and an embedding tensor map. That's how it was originally done in gauge supergravity. And the question was, can you do the same for these generalized diffeomorphism algebras, which are not Lie algebras? And there's a construction that works, and that I think is quite natural. And it's as follows. So first, we have to identify what is the Lie algebra. And since it's a Lie algebra, or it's some kind of algebra of generalized diffeomorphisms, it must be something infinite dimensional. So we construct this as follows. So you start with a usually finite dimensional Lie algebra G0. That is just the Lie algebra of a U-duality group you're considering. So for instance, there's the E7 exceptional field theory that is covariant under the U-duality group E7, 7. So let's think of this as the Lie algebra that's written here. So alpha, beta are the adjoint indices, F alpha, beta, gamma are the structure constants. And then on top of that, I always specify in gauge supergravity a representation space, which I call R0 here. So this is all finite dimensional still. So I have matrices T alpha Mn, where Mn label the representation, the indices of the representation space R0, and they are a representation of this algebra. Okay, so that's the finite dimensional starting point, but now from this I build an infinite dimensional Lie algebra, which we denote by this funny G here, as consisting of pairs of functions. So I have this abstract object zeta, which has two components. It has a vector kind of function lambda m, and so m is the representation index, and sigma alpha, where alpha is the Lie algebra index. And they are functions depending on coordinates ym, which you can just think of flat space with the dimension of the representation space. So ym are just as many coordinates as the dimension of the representation is. So for instance, for E7, this would be 56. So you introduce a lot of extra coordinates in general. Only some of them you actually need in order to describe, for instance, 11-dimensional supergravity. But this is needed in order to write things covariantly. But so far, I just introduced them, no further assumptions. And now I can define a genuine Lie algebra bracket by this relation here. So the bracket between zeta 1, zeta 2 has two components, because these are all pairs. The first component is just the normal Lie bracket of vector fields. So lambda 1, lambda 2 are vector fields. I can build this normal Lie bracket. In the second component, where I have these alpha objects, I have this term here, which is like a transport term, a transformation of the sigmas like scalars. And then I have a non-abelian term which just uses the original Lie algebra structure with F alpha, beta, gamma structure constants. So the claim is that this defines a genuine Lie algebra. You can check that satisfies the Jacobi identity without any funny assumptions. Okay. So that's the Lie algebra. So given a Lie algebra, of course, as I've explained before, or reminded you of before, I have the adjoint representation and also have the co-adjoint representation, which is X on the dual space G star. And since it's dual, it consists of pairs of objects A alpha Bm with the same index structure here, but dual to it. And there's a non-trivial pairing between co-adjoint vectors and adjoint vectors of this kind that is just given by an integral. So you pair up the objects naturally, contracting the indices, and you integrate this, and this defines the pairing between vectors and covectors. And you will have seen a construction like this for the Virasoro algebra, for instance, where we also have an infinite dimensional algebra of one-dimensional diffeomorphisms, and the dual space is defined by the same rules. Okay. All right. Now there's one technical subtlety which I probably ignore because of the lack of time, is that eventually we'll have to impose so-called section constraints, which means that not all the coordinates are actually non-trivial, and which means there can be non-trivial vectors, non-vanishing vectors, that actually still act trivially on everything else. And this in turn defines a certain ideal, a certain subalgebra that is an ideal and that we have to mod out in the final Lie algebra that we think of as the Lie algebra that is the starting point for the embedding tensor formulation. But if you do this, you also have a dual space again, G star, that consists of these pairs of objects. And they have well-defined transformation rules. And now finally, what we need to define the Leibniz algebra is a choice of representation space R of this infinite dimensional Lie algebra G. So this G is now this infinite dimensional Lie algebra I defined before. So now I have to pick a representation space, and what is it? Well, it's this infinite dimensional space of functions Vm of the same coordinates y, where the action of an adjoint vector zeta is defined via this formula. So remember that zeta has two components, a vector lambda m and a parameter sigma alpha. And alpha is the adjoint index of the original finite dimensional Lie algebra, and I can write down this formula, which is, in fact, you can check the representation. And now the embedding tensor map is obtained by this map here. So you start with a vector Vm of the representation space, and you want to make an adjoint vector out of it. And remember, this has two components, is a pair of functions. So the first component is just the original vector Vm, because that's the structure you want. In the second component, you need something that is an adjoint index. So there's one natural operation you can do. You take the derivative of the vector Vm, and you contract it with the original representation matrices in the representation R of the generators T alpha, and that leaves you something with a free index alpha. So that has the right structure. And now finally, you can go ahead and take the formulas of defining the Leibniz product via this general rule we had here, using the representation matrices and inserting the embedding tensor. And then you find this formula here, which, for those of you who have seen it before, actually defines what's called the generalized Lie derivative of exceptional field theory. That's the generic structure, where the constant kappa is just a number that has to be fixed in a case-by-case basis for the different groups. And you can check that the quadratic constraint is obeyed, provided that you impose what's called this section constraint on these derivatives m. So not all of these coordinates are finally active, only a subset of it is active, but using
Olaf,
that. Yeah.
You're already over time. Can you wrap it up?
Yeah, I'm almost. I can wrap it up, yes. Okay, so now here are just a bunch of examples where you can work this out, what this means. So this is for the group ODD, but it's really just specifying the structures for one special case, and you can check that the Lie bracket of double field theory comes out correctly. You can identify now what this frac D is, which in this case is just a normal derivative, what the bullet operation is, which in this case is just a contraction with the ODD metric, and all the structures that I described generally before are here seen again as in a particular case. And then you can go through the list of various groups, E7, E8. E8 is very interesting because here the representation space we have to pick for the embedding tensor construction is just the co-adjoint, it's the dual of the original Lie algebra itself. And that leads to some funny structures that before were not understood well, leading to a Schoen-Simons formulation in 3 dimensions with a double set of gauge vectors based on a Lie algebra defined on the co-adjoint representation space of this infinite dimensional algebra. Okay, let me wrap up now. So I've defined various things. In particular, the most important feature, I guess, was this duality hierarchy, which combined all fields, all p-form gauge fields, including the zero forms, so the scalar fields, into one nice structure, and which gave us, as integrability conditions, the nonlinear field equations of gauge supergravity. So one very intriguing question is whether we can exclude the external metric, G mu nu, in some similar fashion. Here, the metric was just an external object that I had to assume for gauge supergravity, so to define the Hodge dual, for instance. But in exceptional field theory, the metric plays a more non-trivial role, so the question is whether it can be included here. Another thing which has not yet been done is actually to write exceptional field theory explicitly in terms of these structures. For instance, to interpret the potentials for exceptional field theory in this language in terms of an appropriate T-tensor and an H-invariant metric. Another question is whether we could write actions for duality relations, then probably non-covariant actions, perhaps of the type that Henning discussed for the exotic D = 6 theories on Monday. And the sort of the big question always is, the big theme, which eventually is sort of the dream, is to find some big universal algebraic structure that encodes all of these theories in one universal formulation without having to do a split and a dimension by dimension dependent discussion. And so one idea could be that there's some universal differential graded Lie algebra that puts just everything onto the same footing. But that's at this point more a dream than a concrete result. So let me stop here. Thank you very much.
Okay, are there some questions or comments? Okay, one over here.
Thank you. So I have a question about gravity. How far did you go in the dual description of gravity? So you wrote linearized equation on your first slide.
So far in this picture, we have not included gravity at all. So that's why it's one of the points here, to figure out how to include it.
But you say external metric, but at some point you want a dynamical metric, I guess.
Yes, that's what I'm right. By external, I mean we have the split into internal and external. Okay. It's not dynamical versus non-dynamical. That's just the difference.
A related question, in the case of gravity, the duality relationships you wrote were in terms of Christoffel symbol somehow. First order, they involve first order derivatives.
Right, yes.
Now, in the case of exterior forms and the scalar field, the duality relations involve the curvatures, and that's nice because then you control more easily gauge invariance.
Right.
Now, in the case of gravity, there is an equivalent version of duality which is in terms of curvatures, which is not so nice because it involves second derivatives, but which is nice because it's gauge invariant, manifestly gauge invariant. Do you have any thoughts about this difficulty?
I have thoughts, but nothing I can really express coherently. I don't really know. I guess one would have to, in this framework, one would have to need some kind of first order formulation where you introduce more auxiliary fields to make things first order. I guess that's in this particular framework would be needed. But as I said, I haven't really thought about it too much.
Maybe another question unrelated to this, but related to, I think, the third point of on the last slide about non-covariant actions.
Yeah.
Where they are covariant, but not manifestly so, I guess. I mean,
I should have said
I
should have said non-manifestly invariant. Yes.
Okay. And well, there are some thoughts that maybe duality invariance might imply Poincaré invariance. Do you have any idea on that? Or I mean, there are some models which are simple, which indeed exhibit that feature, that the only duality invariant equations you can write within some set of assumptions will automatically be Poincaré invariant, although not manifestly so. So I think it's an interesting idea because duality might indeed be more important than space-time covariant, which would be derived.
Okay, I would be open to that. I can imagine, yes.
Okay, are there some online questions or remarks? Then just unmute yourself and ask.
Yeah, I have one. Can I ask you?
Yes.
Hello? Yeah. So there was some slide somewhere in the middle, which is called derived from differential graded Lie algebra, and there was a differential graded Lie algebra constructed out of a Leibniz algebra with D currently, x2, x1, x0, and so on. Do I understand correctly? This is the counter super algebra, and the differential is the adjoint to the Lie operator, because I think it would be a natural construction, isn't it?
Sorry, I didn't quite understand. Do you understand?
Yeah, that's precisely. This is the picture, right? So you have this differential graded Lie algebra.
Yeah.
Right. Is it the counter algebra, or is it related to the counter algebra constructed out of the vector space?
Sorry, I don't understand. So, what kind of algebra?
Cantor, K-A-N-T-O-R. Okay, sorry.
Well, no, I don't know because I never heard it before. So.
Okay, I understand, right? But there is a construction like that.
Okay, yeah, I should look into it.
Okay. Okay.
Okay, I have also one question at the end. It was a bit fast with this Chern-Simons theory. I had the impression that if one constructs a Chern-Simons theory for a Leibniz algebra, it always becomes equivalent to normal Chern-Simons theory. So I mean, if I thought about, at some point I thought about it.
Yeah.
How does it? How is your? Maybe you can go back to this Chern-Simons theory you had and explain a bit.
Yeah, I didn't actually write it in detail, but it is true that you can always. It's probably correct to say that it's always equivalent in the suitable sense because. So, for instance, where do we have it? Here, for instance, yeah. So you work with the Leibniz algebra, which has a symmetric part, so it looks like something more general than in Lie algebra. But the symmetric part acts trivially via this sort of generalized adjoint action. And correspondingly, there's an extra redundancy in the formulation. So there's an extra gauge symmetry of this seemingly generalized Chern-Simons theories. So it's, I think, always true that you can indeed gauge fix or remove this extra redundancy, and then you're back to a normal Chern-Simons kind of thing. So in that sense, it's probably correct, what you said, that it's always equivalent. But the point, at least that's the way I understand it, is that in order to go back, so in order to reduce this extra redundancy, you have to break up the manifest duality invariance. So the duality covariant formulation, where all indices are nicely contracted, then requires these higher algebras.
So your Leibniz algebra here is infinite dimensional, right?
Yes, in this example, so in gauge supergravity they're finite, as you very well know, they're finite dimensional, but here they're infinite dimensional, yes.
And this infinite dimensional one is what is having these variables y?
Yeah, so they are functions, that's why they're infinite dimensional. They are functions of some set of coordinates y.
And if one takes this Leibniz algebra and quotients out the ideal generated by symmetric elements,
yeah.
Does it give something like does it have a nice description, this Lie algebra, this quotient Lie algebra from the Leibniz algebra, or it's somehow ugly?
For me, it's somehow ugly. I mean, maybe that's just my personal...
No, but it cannot be described again like in a similar fashion. That's what
I don't think so. I think you can, of course, in principle do it and say it, but I don't think, in terms of these formulas, how we like to work with it...
It would lose some covariance, you say?
I think you would
lose locality, maybe?
Yeah, maybe.
Okay.
Right.
Okay, any further questions or remarks? If not, thank you very much again.